Welcome back to Cosmos in a Pod. It's our space and astronomy series, and today we're diving deep into globular clusters.
How fascinating.
These tightly packed spherical, yeah, they're spherical, collections of stars that orbit galaxies like ancient guardians.
Yeah.
They really are guardians.
Beautiful.
So, I mean, have you ever looked up at the night sky and wondered about those tiny points of light?
All the time.
Well,
absolutely.
Some of them are actually massive clusters,
right,
containing tens of thousands
incredible
to millions of stars crammed into a space just a few light years across.
Yeah, it's mind-boggling, isn't it? To think that these clusters have been around for billions of years.
I know. So to start off, can you give us a little Astronomy 101 on globular clusters? What exactly are they, and how do they differ from, say, the scattered stars we see in the night sky?
Yeah, great question. So you can think of globular clusters as these tightly bound families of stars held together by their mutual gravitational attraction. They're incredibly dense, with stars packed much closer together than in other parts of a galaxy. Imagine our sun having thousands of close neighbors, all within a few light years.
Oh, wow.
It's a very different environment from the relatively sparse distribution of stars in our galactic neighborhood.
So it's like comparing a bustling city center to a quiet suburban neighborhood.
Exactly. And unlike open clusters, which are much looser and tend to disperse over time,
Right.
these globular clusters are remarkably stable and long-lived. We're talking billions of years.
Wow.
This longevity is due to their strong gravitational bonds and the sheer number of stars they contain.
Billions of years. So that means some of these clusters have been around since the early days of the universe. So if they're so old, what kind of stars do they contain? Are they similar to our sun?
That's where it gets really interesting. The stars in globular clusters are predominantly what astronomers call population 2 stars. These are ancient stars, much older than our sun, and they have a fascinating story to tell.
Okay.
They formed in the early universe when heavy elements were much rarer. Think of it this way. By heavy elements, we mean anything heavier than hydrogen and helium, the two lightest elements.
Got it.
So these population 2 stars have a lower metallicity than younger stars, like our sun. They're like living fossils, preserving the chemical composition of the early universe.
That makes sense.
Yeah.
So by studying these stars, we can learn about the conditions that existed billions of years ago, right? It's like looking back in time.
Precisely. And that's why astronomers are so fascinated by globular clusters. They're like windows into the past, offering clues about the formation of galaxies and the evolution of stars.
Now, you mentioned that these clusters orbit galaxies.
Yes.
Where exactly do we find them? Are they scattered throughout a galaxy like sprinkles on a cupcake?
Not quite. They tend to congregate in the halo of a galaxy. Imagine a vast spherical region surrounding the main disk of a galaxy, like a halo.
Oh.
That's where you'll find most globular clusters, forming a sort of cosmic shell around the galactic core.
So they're not hanging out in the bustling galactic disk where most of the star formation happens.
Exactly. They're more like ancient observers watching from the outskirts as the galaxy evolves.
I see, I see.
Our own Milky Way galaxy has about 150 to 180 of these globular clusters in its halo.
Wow.
You might have even heard of some famous ones like Omega Centauri,
Oh, yeah.
the largest globular cluster in the Milky Way.
Omega Centauri, that rings a bell. It's massive. Right?
Absolutely. It's so big that some astronomers believe it might be the remnant of a dwarf galaxy that was swallowed up by the Milky Way long ago.
Whoa.
Now let's talk about how these clusters formed.
Okay, wait. Before we get into that,
Yeah.
I have a question about their size.
Okay.
I'm trying to picture these things in my head. How big are we talking?
Ah, good point. Yeah, it's easy to get lost in the vastness of space. Globular clusters typically range from about 50 to 300 light years in diameter.
Okay.
To put that in perspective, a light year is the distance light travels in a year, which is about 5.88 trillion miles. So these clusters are incredibly vast, containing hundreds of thousands, sometimes even millions of stars, all bound together by gravity.
That's wild.
Now, let's dive into how these cosmic giants came into existence. It's a story that goes back billions of years to the early universe. Okay, so picture this. The early universe, just a few 100 million years after the Big Bang. It's a chaotic place, filled with swirling clouds of gas and dark matter. Gravity is starting to pull these clouds together, causing them to collapse and heat up, and within these dense, hot regions, the first stars are born. And some of these early stars bound together by gravity formed the seeds of what would become globular clusters.
Whoa, so these clusters are like relics from the universe's infancy.
Exactly.
But how did they manage to survive for billions of years while everything else around them was changing?
Well, it's all about gravity. The intense gravitational attraction between the stars in a globular cluster creates a remarkably stable and resilient system. Think of it as a giant cosmic dance with all these stars swirling around a common center of gravity. And as they interact gravitationally, they exchange energy. Some stars gain energy and move outwards, while others lose energy and sink towards the center.
So it's a bit like a chaotic mosh pit, but with stars instead of people.
Yeah, a very apt analogy. And this ongoing gravitational interplay contributes to the cluster's longevity, helping it to withstand the disruptive forces of the evolving galaxy around it. Now, despite this remarkable stability, these clusters aren't static. They evolve over time,
Right.
and that's where things get even more fascinating.
Okay, I'm all ears. What kind of evolutionary changes can happen in these clusters?
One intriguing process is called core collapse, which we touched upon earlier. As stars lose energy and drift towards the center, the cluster's core becomes incredibly dense. Imagine millions of stars packed into a relatively small space.
Wow, that must be an incredible sight. But wouldn't that lead to a lot of collisions between stars?
You're right. That's exactly what can happen. And those stellar collisions can lead to the formation of some rather unusual and fascinating stars. Remember those blue stragglers we talked about earlier? The ones that appear much younger and hotter than their neighbors? Well, they're thought to form through stellar mergers or mass transfer in binary star systems. It's like giving an old star a second life.
So it's a cosmic fountain of youth hidden within these ancient clusters. That's incredible.
Indeed. And it's a testament to the dynamic nature of these seemingly unchanging objects. Another evolutionary process that can shape these clusters is tidal stripping, which occurs when a globular cluster passes too close to the galactic center.
Okay, remind me what tidal stripping is again. I'm still trying to wrap my head around all these cosmic forces.
No problem. Imagine the globular cluster as a big, fluffy ball of cotton candy. Now imagine you swing that cotton candy near a giant fan. What happens?
The fan's wind would blow away some of the cotton candy.
Right. Exactly. And in a similar way, when a globular cluster ventures too close to the galactic center, the intense gravitational forces of the galaxy can pull away stars from the cluster's outer edges. It's like stripping away layers of an onion.
So it's a cosmic tug of war between the cluster and the galaxy.
Precisely. And sometimes the galaxy wins, leaving the globular cluster a bit smaller and less massive than before. But even with these ongoing changes, these clusters have managed to survive for billions of years, offering us a glimpse into the universe's distant past.
You know, it's amazing to think that these clusters, filled with ancient stars, are still evolving and changing. It reminds me of how even the oldest trees on Earth continue to grow and adapt to their environment.
Yeah.
But you mentioned earlier that globular clusters aren't just visually stunning. They're also incredibly valuable to astronomers.
Right?
Can you elaborate on that? What kind of insights do they provide?
Absolutely. Globular clusters are like cosmic laboratories, offering astronomers a wealth of information about the universe. For one thing, they've played a key role in helping us determine the age of the universe.
Oh, okay. I'm intrigued. How do these clusters help us figure out how old the universe is?
Well, remember how we talked about the stars in globular clusters being some of the oldest stars in the universe? Well, by carefully studying their properties and evolution, astronomers can estimate their ages. And since these clusters formed relatively early in the universe's history, their ages provide a lower limit on the age of the universe itself.
So it's like using the oldest members of a family to trace back the family's history.
Exactly. And by analyzing the light from these ancient stars and applying sophisticated models of stellar evolution, astronomers have been able to refine our understanding of the universe's age, which is currently estimated to be around 13.8 billion years old.
13.8 billion years. That's mind-boggling. And it's all thanks to these ancient stellar clusters. It's amazing how something so seemingly distant and insignificant can tell us so much about the grand scheme of things. What other secrets do these clusters hold?
Well, one of the most intriguing areas where globular clusters have made a significant contribution is in the study of dark matter.
Ah, dark matter. The mysterious substance that we can't see but know must be there because of its gravitational effects. How do globular clusters help us unravel this cosmic enigma?
Well, it's all about gravity and how it affects the motions of stars within the cluster. You see, the way stars move in a globular cluster is influenced by the total mass of the cluster, including both the visible matter, like the stars we can see, and the invisible matter, like dark matter.
So even though we can't see dark matter directly, we can detect its presence by observing how the stars in a cluster behave. That's clever.
Exactly. Astronomers carefully observe the speeds and orbits of stars within globular clusters, and by analyzing these motions, they can calculate the cluster's total mass. Then they can subtract the mass of all the visible stars and gas. Whatever mass is missing must be due to dark matter.
So it's like a cosmic accounting problem,
Right.
where we're trying to balance the books of the universe.
A very elegant way to put it. And this technique has provided some of the strongest evidence for the existence of dark matter. And it's helping us to understand its distribution within galaxies. It's amazing what we can learn from these ancient stellar systems.
It really is. It makes you realize that even in the vastness of space, everything is connected. But as much as we've learned from globular clusters,
Hmm.
there are still some lingering mysteries.
Right.
What are some of the questions that astronomers are still grappling with?
Oh, absolutely. Despite all our advancements, the universe loves to keep some secrets. For one, we still don't have a complete understanding of how these clusters formed. Was it simply from those early clouds of gas collapsing? Or did some clusters form from the mergers of smaller galaxies, their stars combining into these dense spherical families? It's a cosmic mystery of origins.
So their origin story is still being debated. That's fascinating. It's like trying to piece together a puzzle with missing pieces.
Exactly. And this question of their formation is closely tied to the role of dark matter. We know dark matter must have played a significant role in the early universe, but how exactly did it influence the formation and evolution of globular clusters? That's another piece of the puzzle we're still trying to solve.
Dark matter always seems to add a layer of complexity, doesn't it?
Mhm.
It's like the invisible hand shaping the universe.
Indeed. And speaking of invisible things, another intriguing question revolves around the presence of black holes in globular clusters.
Ah, black holes. You mentioned earlier that some astronomers suspect there might be intermediate mass black holes lurking in these clusters, right?
Yeah.
The ones bigger than stellar mass black holes, but smaller than the supermassive ones at the centers of galaxies.
Precisely. They're like the missing link in the black hole family tree. But finding conclusive evidence for these elusive objects has been a challenge. Black holes, by their very nature, are invisible. They don't emit light, so we can only infer their presence through their gravitational effects on nearby matter.
So it's like trying to find a ghost in a crowded room.
A very apt analogy. However, astronomers are developing new techniques and using powerful telescopes to search for telltale signs of these hidden black holes. For example, they're looking for stars orbiting very rapidly around an unseen object, or for bursts of X-rays that might be emitted as matter falls into a black hole. It's an ongoing area of research, and hopefully we'll have more answers in the future.
It's like a cosmic detective story, with astronomers playing the role of Sherlock Holmes, searching for clues to unravel the universe's mysteries.
Indeed. And it's this sense of wonder and the pursuit of knowledge that drives us to explore the cosmos and try to understand our place in it.
Well, this deep dive into globular clusters has been truly mind-expanding. I feel like I've gained a whole new perspective on these ancient stellar families.
It's been my pleasure to share this journey with you. It's amazing to think that these clusters have witnessed billions of years of cosmic history, and they continue to hold secrets that we're only beginning to unravel.
It makes you realize how much more there is to discover out there. Before we wrap up this cosmic adventure, I want to remind our listeners to subscribe to Cosmos in a Pod and check out our YouTube channel for more fascinating content about space and astronomy. We explore everything from black holes to exoplanets to the search for extraterrestrial life.
And if you enjoyed this deep dive, please share it with your fellow space enthusiasts. The more people we can inspire to look up at the night sky and wonder about the universe, the better.
Until next time, keep exploring, keep those cosmic questions coming, and never stop looking up.